All right, good morning, everyone. My name is Paul Daniel Lee, and today I'm going to be talking to you about a new feature in ZFS that I've been working on called AnyRAID VDEVs. So who am I? As I said, my name is Paul Daniel Lee. I've been working with Clara Systems for about a year now, but this is my 11th or 12th developer summit, and I presented a couple times in the past, and I'm excited to be doing so again. So let's talk about ZFS a little bit. ZFS is used by really a broad array of people, right? We have users up at the enterprise scale deploying racks and racks of servers. They have hard drives by the box. They deploy everything at this huge scale, very efficiently, big budgets, procedures, the whole 9 yards. We have mid-scale users, right? We have Capital Auto Group deploying, keeping track of their sensitive and important data on their systems at a professional scale, but not quite at the enterprise level of some of the vendors that use ZFS. And then we have amateurs and enthusiasts. I'm sure there are a lot of people here who have a server sitting under a desk somewhere with some hard drives in it that they run for the love of the game. I know I do. And all of these different use cases have different constraints and requirements when it comes to how they use ZFS, what they use it for, and the things they care about most. One of the things that a lot of people who use ZFS care about is reliability. This, I think, is probably one of the main reasons that people use ZFS, its ability to protect and preserve your data, even when a lot of things go horribly wrong. And ZFS has a lot of different ways to do that. There's a lot of VDEV type options, right? We can do mirror VDEVs and preserve your data that way. There's RAID Z VDEVs, which have better space efficiency, but have other trade-offs. DRAID is the sort of the newer hotness, although it's been around for a little while now, expanding the RAID Z capability and giving it more interesting features. One odd duck is the copies property, which lets you set at a per data set level and store multiple copies of critical data, but it has its own little trade-offs that we'll talk about. And the nice thing about all these reliability tools that ZFS has built into it is that they're simple to use. You create your VDEVs, you set them up, and then they just keep working. They're performant. They give you good read speeds, good write speeds. They parallelize everything across the disks. They do everything you want from that perspective. And they're effective. They prevent data loss. You can lose a hard drive and everything keeps working, and you can do online resilvers, everything works, and it's all effective and efficient. But there are some restrictions to these things. So all of the VDEV technologies that I talked about require that all of your disks be of the same size, right? If you have a mirror set up, all the disks have to be the same size in the mirror so that you can write to the same place at each of the disks and store all the data redundantly. If you're working at enterprise scale, that's fine. You bought a box of hard drives that are all the same make and model. You can swap them out. You can plug in new ones. You're going to be fine. If you're working on a slightly lower scale, this gets a little bit more expensive, right? If I have a server in my apartment, which I do, running a RAID Z device, I can't just swap out a single drive and make it bigger. I have to swap every single drive for a larger one. And so upgrades become a more expensive and more time-consuming process. The expansion can be slow, right? If you want to expand all those drives, you have to swap out each one for a bigger disk and resilver each one along the way, and that takes time. Or if you want to do RAID Z expansion, we have to reflow all of the data in your RAID Z device. And so all these things take a little while. You can't shrink these devices. If you realize later that you need to take some of your drives and use them in a different appliance or in a different application, ZFS storage pools mitigate this to some extent, since you can partition up your space however you want. But if you need to move it somewhere else entirely, you can't really do that without permanently giving up some of your parity in that device. And all this combines together to create sort of a higher administrative burden, right? There are rewards, obviously. These things are worth using, but you do have to take into account that things are going to be a little bit more complicated to administer. The copies property doesn't have a lot of these same trade-offs, but it also doesn't provide guarantees in the same way that mirrors and RAID Z do. Copies tries to store the multiple copies of your data on different devices, but it's not guaranteed to do so. And it also only provides sort of mirror-like parity where it can store multiple full copies of the data. So there's some space in here for improvements. And the solution that we came up with, in particular for the problem of disks of all having to be the same size, but it also has other benefits, is AnyRAID. This is a new VDEV type in ZFS. It supports all the normal things that you want to do with VDEVs. You can read to it, you can write from it, you can do resilvers, you can do all the fun stuff that normal VDEVs can do. And it provides either mirror-like parity or RAID Z-like parity. configurable at the time when you create the device. And the big feature that it supports is you can have heterogeneous disks. You can have a mix of 10 terabyte drives and 5 terabyte drives and 1 terabyte drives all working together to provide space. And you can actually take advantage of almost all the space on all of those different devices. And then there's some other cool new features it offers, like online expansion, contraction, and then some more that we're going to talk about. So this is the syntax to create a pool using AnyRAID VDEV. You can see it says AnyRAID because it's AnyRAID, and then RAID Z tells you that it's or the RAID Z style parity. RAID Z1 because there's one parity drive, and then the :3 is there's one parity drive and 3 data drives in sort of a conceptual space. But then you can see there's a lot more than 4 disks here. There's actually 7 disks that are part of this device. So we're going to talk about how that works and how all that space gets used and combined together to provide this larger VDEV. So in order to understand that, we're going to take a little bit of a step back and talk about how mirrors and RAID Z work at a high level. This is just going to be a quick summary. Most of you are probably familiar with this. But the way they basically work is that you have the VDEV layer of ZFS that takes these logical IOs. The VDEV presents some block of space to the rest of the system, and then the system does its allocations in that space. And then when it comes time to do IOs, they come down into the VDEV code, and the VDEV code splits those logical IOs into separate physical IOs. So on the left, you can sort of see what mirrors look like. You take one logical IO and turn it into multiple physical IOs, all of the same size, all doing the same thing on the different devices. On the right is sort of how RAID Z works. You have one larger logical IO that gets broken down into small pieces, and then each of those pieces goes to a different drive. The one outlined in red is to represent the parity drive. This is all not how the ZIO tree actually works. The ZIO tree is a nightmarish tangle of weeds sometimes, but this is just sort of a simplified depiction to help understand the high-level concept. So if we look at this in a little more detail, when you do a mirror IO, right, you have your logical IO, and then the physical IOs are sent to separate devices all at the same offset, right? They go to drive A at offset X, drive B at offset X, drive C at offset X, and they're all sort of stored in the same place on each of the drives. That's why they all have to be the same size. For RAID Z, this is sort of accurate as long as everything's in a single row. Again, we're simplifying to sort of get the idea across. But again, you can see that, all of the different parts of the IO end up within a single row of the RAID Z device. They all end up at roughly the same offset with each other. And so what if we could be a little more flexible? What if we didn't have to store all of the data at the same offset on every disk? What if we had some sort of layer of indirection in the middle that would allow us to move the data around and store it in different places on different disks? And could we use that to get better space efficiency? And so the solution for that is called tiles in AnyRAID. Every disk in the AnyRAID VDEV is broken into these tiles. The tiles are the same size on every child, so the children all sort of look the same from that perspective. And then when it comes time to do an IO and use these actual tiles, we allocate the physical tiles from the child disks and stripe them together into logical tiles. And then the logical tiles are combined together to form the block of space that represents the top level VDEV. And since we have this model where you have the stripes that work together to form the bigger VDEV, but the physical tile location is more flexible now, we can preferentially allocate the physical tiles from the larger child devices. And that way we can use those devices more and try to take advantage of all of the space on all of our different devices. So let's look a little bit at what this tile process looks like. So you have your AnyRAID VDEV and you do an allocation on it. You go to write some data on it at the first offset on the VDEV. The AnyRAID code sees that and it goes, okay, I need a physical tile to back that logical space. So let me allocate some tiles, enough tiles to represent the stripe, and on our largest disks. In this example and the ones going forward, I'm going to be using that sort of AnyRAID Z1:3 model, which is a 4 wide stripe. And so the first allocation it does is these 4 disks. Oop, that's not what I want to be looking at right now. Thank you. Where did it go? Here it is. So it comes along, it does its allocations from the first 4 largest disks. Everything's hunky-dory. When we do reads and writes to that area of space, we write to those 4 physical disks. Some new writes come in. Now it's time to allocate another tile. And so this time, rather than just picking the first 4 disks, we pick the 4 disks with the most free space. And you can see that's 1, 2, 3, and 5, since 5 now had more free tiles than 4 did. Time goes on, we do more allocations. This keeps going. And you can see that we're sort of slowly using the larger devices faster than we use the smaller devices. And we sort of, as the tiles get allocated, we build this structure up and we allocate more and more space from these bigger devices. And then eventually, as the smaller devices become the ones with the most free space, we start taking advantage of those as well. And so you get this sort of gradual buildup of all these tiles filling up all of the different child devices equally, and that way you get to leverage all the space that's available in the pool. You'll notice that a stripe of any given color is always across different physical devices, and that's so we provide the reliability guarantees that CFS care about, right? The yellow blocks are all on different devices, the blue blocks are all on different devices, the green blocks are all on different devices. Sort of, there's only so many colors, so there's some similar looking colors, but I hope the idea comes across clearly. And this allows us to preserve the requirements of mirrors in RAID Z, where if you lose any one of these devices, you're only going to lose one tile of a given color. And in that way, we preserve the same reliability that RAID Z would give us, where you can afford to lose any one of your devices, and we can still reconstruct all of your data using the parity information that's part of RAID Z. And the same would be true of mirrors if this was a 4-way mirror setup. So there's this sort of diagram is the picture version of something that we call the tile mapping, which does the mapping from these logical tiles that make up the VDEV space to the physical tiles that are stored on the disk. The AnyRAID VDEV code uses that tile mapping to convert the ZIOs that it receives from the logical layout that the rest of the system sees into the custom physical layout that lets us do this space balancing. And that mapping grows as we allocate the new tiles. And because it grows as we allocate the new tiles, that means that you can add new disks, and that new space will be taken advantage of when that happens. But the mapping that I just talked about is very important, right? This is the kind of metadata in ZFS that we usually store in the MOS, because it's sort of core part of how the pool works, how you read the pool, how you access the pool. But because the MOS is stored in, the normal VDEV space, you can't read it without this mapping. This mapping is sort of necessary in order to read any of the data off of the pool. So we have to load this first before any other reads can happen from this VDEV. And so the question is, how do we store this data? Where do we put it in such a way that this can be accessed before everything else? So there's a new on-disk structure called the tile map. And the way that this works is that we allocate a region after the first 2 labels in ZFS and before the sort of data segment where we store all of the normal data in ZFS. We just, at creation time, allocate a chunk of space there and then use that to store this critical metadata. We store the mapping between the logical and physical tiles there. The actual, tile 1 is located at these places, tile 2 is located at these places, and so on. And then there's also some other critical metadata that you use to parse that and process it and understand it. Because ZFS is a copy on write file system, we never want to overwrite anything in place. And so that we actually store 4 full copies of this tile map, and we rotate through them during each TXG in the same way that we rotate through Uber blocks. So if, even if you have something go wrong while you're syncing up a tile map, we can still roll back to the previous transaction group, and that full tile map is there, untouched and ready to be used. And because this is such critical metadata, we actually store it fully replicated on every single disk. Every disk has a full copy of the tile map. Because if you did lose this data structure somehow, you would be unable to read the data on any of your pools or any of your disks in the pool. You'd have to do some sort of very complicated reconstruction process that I'm not sure how it would work. So we fully replicated across all the devices with maximum reliability, since it's so important. The size of the tile map on any given disk. So each copy of the tile map is 64 megabytes, and there's 4 copies of them. So they combine together to be at about 256 megabytes of space. On modern hard drives, that's not that much. So it felt like an acceptable amount of space to use. And that guarantees the storage for the full size of the mapping that AnyRAID supports. AnyRAID supports up to 256 drives per top level AnyRAID VDEV. And each of the drives can have up to 65,536 tiles on them. And so that comes with some limitations that we'll talk about a little bit later. But if you do the math, that all combines together and it all fits in exactly 64 megabytes. I've talked about the tiles, how they're the same sizes on all the disks. The specific size of those tiles is tunable. There's a bunch of options, but the defaults are that it is either a 64th of the size of the smallest disk that's part of the VDEV at creation time, or 16 gigabytes, whichever is bigger. We want to store entire metaslabs together within a single tile so that we don't have IOs like going across tiles and then having to split those and create more complicated ZIO trees. So 16 gigabytes felt like a reasonable floor, and 1 terabyte is a pretty reasonable size for hard drives in the modern day. What that does mean, in conjunction with the 65,000 tile limit that I mentioned, is that if you have a 64th of the smallest disk as the tile size, then the largest disk that you can use all the space of is 1,024 times the size of the smallest disk that was part of the VDEV at creation time. So if you create a VDEV with, some 5 terabyte drives, a 10 terabyte drive, and a 1 terabyte drive, that AnyRAID VDEV, for now at least, we can talk about future mitigations, that AnyRAID VDEV can't support a physical drive larger than a petabyte, which will probably be fine for a while. In memory, we store this tile mapping in an AVL tree, nice, easy, reliable data structure, and it doesn't get that big, so we don't need anything more complicated than that. And then the AnyRAID VDEV layer uses that AVL tree to convert the logical IOs that come in, figure out where the physical tiles that back that data are stored on disk, and then uses that to dispatch IOs to the existing mirror and RAID Z code. So we don't have to re-implement any of the parity stuff. We don't have to do any of the sort of healing logic or reconstruction logic or failing over to different devices logic. All of that we get just by calling into that code directly. What can this feature do aside from storing your data? Well, it can do all this normal stuff that you want VDEVs and ZFS to be able to handle. It supports resilver, just like you'd expect. We can do scrubs, we can do checkpoints, all the normal things that you'd expect ZFS to be able to do. For mirror parity, we support linear resilvering, the same way mirrors do. We don't for RAID Z because the way RAID Z stores its data is not really amenable to linear resilvering, but that's true of actual RAID Z as well. For checkpoints, you can do checkpoint rollbacks just like usual. We don't store a separate full copy of the tile map, and the tile map isn't in the MOS. So we have to have some special stuff for handling checkpoints in the tile mapping. And the way it works is it rolls back the space up to the sort of highest allocated logical tile that we save when the checkpoint is taken. That works fine for the current design. There may be augmentations to that for the future, but there's plenty of space in the metadata to store more interesting information about that. There's exactly 2 caveats that I am aware of, which is trim and initialize. The way trim and initialize work is a little bit interesting. You take the logical space within the VDEV and then it converts it to a physical offset for each of the children, which is fine and good, except that for the space that isn't mapped yet, that isn't backed by physical tiles, there is no corresponding physical location for that logical space yet. And it would be very silly if anytime you did a trim or initialize, we immediately allocated all the tiles and pinned all the space and made it impossible for you to take advantage of new disks in the future. So trim and initialize will just stop at the point where you've stopped mapping from logical tiles to physical tiles. It won't operate on any physical space that hasn't been mapped yet. And in practice, that isn't that huge of a concern, right? Trim is mostly used for secure erase or other things like that. And there you're mostly going to be care about doing that to things that you've already allocated as part of the pool. So any space that you've already written as part of the pool, trim will happily go and write all of that. Anything you haven't written yet, trim won't deal with, but you can clear that before you add it to the AnyRAID VDEV, hopefully. Initialize was originally intended to work more with thin provision devices and cloud devices and things like that. But when you're creating those devices, you get to specify what size they are. And so the advantages of AnyRAID, where it can support these different size disks, are not as essential for that use case. And so it's all an acceptable trade-off to not have initialize work for the entire physical VDEV. These things could be augmented in the future. They're not by any means permanent problems, but for the initial implementation, these are the caveats. Let's talk about some of the other new things it can do that other VDEVs can't do or can't do in the same way. So one of the things is expansion. With this architecture, it's very easy to add new drives to the VDEV and have that space be available. You're not changing the sort of parity or width of the way we actually write out the data, like the way that RAID Z expansion works. Um, we simply add a bunch of new tiles that get used to back the space that are for more logical tiles, and it makes more space available in the VDEV. So as an example, we're looking at basically our same VDEV from earlier, but it's now getting very full, right? We're running very low on space, and we want to add another physical device to back the pool so that we can have more storage. Um, so you can see we just slap a new drive onto the side. We split it into tiles the same size as all the existing tiles and all the existing VDEVs. And now all of these tiles are available to use and do allocations from, and that space is immediately available to use as part of the AnyRAID VDEV. But there is a caveat here, which is that because this pool got so full before you added the new device, even with all these new tiles, we can't actually store more than a couple of new logical tiles in this whole thing without doubling up and using the same drive multiple times, which would break our reliability guarantees, which we don't want. So we need some way, or it would be really nice if we had some way to move tiles from the existing disks onto this new disk that has all this free space. And by doing that motion, we could free up space on all the different devices and make it easier to allocate stripes across all the different disks. And so that capability is rebalance. This lets us move tiles from very full disks to very empty disks. It's helpful, for example, in this case, when you're attaching a new large disk. But it can also be useful, in other cases that we'll talk about. And it helps us always take advantage of all the space that all the disks have available. So you can see, we can only allocate about 2 more tiles from this, right? We can get in this 4 wide model, we allocate 1 from our biggest disk, and then 1 from each of the first 3 disks, 1 from the big disk, 1 from each of the next 3 disks, and then we're done. But if we rebalance, we can pull tiles out of the old disks, move them to the new disk, and then there's space available on each of these different child disks, and we can start to allocate more stripes across all of them. And suddenly all of your space is available for use again. And because of the way that these tiles work, it's easy to move whole tiles at a time, right? You're just moving the whole thing from one spot to another. And because this happens at the VDEV layer and we have the mapping that keeps track of where all these different tiles are stored, we don't have to do block pointer rewrite. We don't have to keep the sort of complicated indirection tables that device removal has to do something similar to this. We have some metadata that we keep track of, but because we're operating in these big contiguous chunks, it always stays a pretty manageable size and is easy to keep track of and store efficiently. So you have this device, it's doing great, it's doing good work for you, you love it, but it's time for one of your disks to go away. Maybe that disk is getting old and you're worried about failing, and you don't really need all of the space that your device has available, so you want to get rid of it before it fails and then you have to replace it with a new disk. Or maybe you want, that smaller device is an SSD or something that you cobbled this thing together out of spare parts, and now you want to use that SSD for a cache or for a special device or some other purpose. You want to take that disk out and replace it with something else. But you don't necessarily need to put a new disk in its place. You don't need that extra space. And so this is another new feature in AnyRAID. We can do contraction, which lets you remove individual child disks from the AnyRAID VDEV. Once that removal happens, there's no extra indirection metadata. This is all handled by the tile mapping that's part of the AnyRAID VDEV. Except during the removal process, there will be some extra stuff that's stored to keep track of the progress of the tile motion and all that stuff. But that's a relatively small amount. That's pretty ephemeral. And as I mentioned before, we get to do nice, efficient sequential copying of all this data because it's all stored in these big contiguous chunks, and we're all moving it to the same place together. So we get to do big read IOs and big write IOs, and everything gets to proceed nice and quickly. So you can see we have our logical device there with its 4 allocated tiles, and we take those and we put them on different disks where we don't already have something of the same parity. And that way we get to ensure that we can remove this device and you keep the same parity you were working with, but you've shrunk your VDEV, and you can now use that disk for something else or just get rid of it if it was getting old. There's some other new things that are just part of adding any new feature to ZFS. There's new ZDB printing functionality that lets you print out the AnyRAID map and display it. It does it in this nice sort of tabular format. I spent a little while playing with Unicode table making characters to make it look nice and pretty. There's Z-test and ZFS test support. So Z-test can now create AnyRAID VDEVs and do all sorts of weird operations to them as part of the testing process. And there's a bunch of new stuff in the ZFS test suite to test it. And then there's some new VDEV properties for the AnyRAID VDEVs themselves. The tile capacity, the number of tiles that you could allocate on the AnyRAID VDEV or one of its children, the number of currently allocated tiles in the whole AnyRAID VDEV, or again, in each of its single child devices. And then the tile size is also accessible as property. So all these things can be used programmatically if you need them for whatever purpose, or if you're just curious to see what it looks like without having to parse the big ZDB output. So where is the project now? The mirror parity implementation and sort of all the core infrastructure is currently up for review on the OpenZFS GitHub. The RAID Z parity implementation, adding the sort of parity style or RAID Z parity style and the couple of extra features that go along with that, is done internally. I have it working and I can create pools with it and everything. But I'm waiting for the initial stuff to land before we open a review with the new stuff. Rebalance is what I'm currently working on right now. I have a bunch of the infrastructure, the sort of user-facing infrastructure in place, and now it's time to actually do the sync tasks and the progress tracking and the data motion and all that stuff. And then once rebalance is done, it'll be time to do device contraction because it gets to leverage the data motion the rebalance uses. Expansion is actually part of the mirror parity implementation. That already works, but you can't do the rebalance yet. So those are in different phases for implementation reasons. And then what's next? So the first thing is obviously finishing the review for the mirror parity implementation. Some folks have already taken a look at that, and I'm extremely grateful to those people, but I would love if more people want to take a look at that and get eyes on it. I want to finish the ongoing tasks, the expansion and contraction and rebalance and all that stuff, and then get those ready internally and then post upstream reviews for those once the original review is done. And then there's a bunch of ideas for future development. This initial stuff that we're working on at Clara, the future development stuff, maybe we'll work on, but other people are also absolutely able to take this on. I have a lot of ideas. We could remove some of the limitations in the current design, right? The 256 drive limit and the 1024x size limit. There's a couple different ways to go about this. We might need to increase the mapping size or handle running into that limit. I think we could do something where instead of having this sort of fixed rectangle of space that you're allowed to use with, this many drives and this much size in each drive, there would instead be a limit to the A size of the VDEV, where you could use any number of drives and any size of drives, but just only so many tiles in total until we would fill up the mapping. I haven't played with implementing it, but I think something like that would work. So if people want to play around with that idea, they absolutely can. Right now, the tile map is stored uncompressed. We don't compress it to save space, but we could compress it. And if it compressed well enough, one, that might let us increase some of those limits. And two, we might be able to store it in different locations. Right now, we have this sort of dedicated chunk of space at the start of each VDEV, but taking advantage of the new large label format that Alan's going to be talking about later, maybe we could store it in some of that space or in some of the reserved space as part of that. And that would let us do some more interesting things and be a little more efficient. Right now, you can't do normal RAID Z expansion if you're using AnyRAID with RAID Z style parity because it was complicated and I didn't feel like dealing with it. But that is certainly an augmentation that could be made for the future, and that would let you increase the width of your stripes going forwards. Right now, when we do contraction, we can only move whole tiles around. Even if you've freed almost everything or literally everything from a tile, the tile never sort of gets unpinned by the AnyRAID code. But one thing we could do going forwards is use something like device removals, indirection mappings to pull little pieces out of the tiles that are pinning them and move those into other sort of logical places in the VDEV. That would let us do much better contraction. It would let us shrink devices way down. It would let us, instead of doing full rebalances where you move all the data to a new disk, just shrink the number of tiles that are actually effectively in use, and in that way take advantage of the space more efficiently. There's a bunch of performance work that could be done. In the initial version, we're very focused on using all the available space that's in the VDEV. And so that means you don't always use all of the child disks, right? If you think back to the diagram from before, when you only have one or two physical stripes allocated, you didn't actually have something on all of the different disks. And so you weren't necessarily taking advantage of the bandwidth of all of the disks that you had in your VDEV. And there are ways to improve that in even the initial version, and I have some stuff that I'm playing with for that in the current pull request. But ways to improve it going forwards is when we're doing allocations in ZFS, we have a rotor that sort of picks between the different top-level VDEVs to decide where to put the data. We could have a rotor within the VDEV layer to sort of try to pick between different parts of the VDEV that are backed by these different physical tiles and use that to try to do a better job of distributing our IOs across the tiles and take better advantage of all the disk bandwidth that you have available. There are limits to this, right? At some point, if one disk is much bigger than the others, you have to do a lot more writes to fill up that disk, and so that disk will eventually sort of be the bottleneck. But there's improvements that could be made there. Right now, we always write out the full copy of the tile map every TXG just for simplicity. But we could skip writing out blocks that haven't changed, or even skip writing out the whole mapping if it hasn't changed. And that would reduce sync times a little bit. It doesn't take that long for normal TXG syncs. But when you're doing like an export or forcing a bunch of transaction groups at the same time, this can lengthen your TXGs by a little bit and make those things a little slower. So there are some changes that could be made there to skip some of that stuff that just aren't in the initial implementation for simplicity. And then another cool idea is doing VDEV conversion from an existing VDEV. Right? If you think about, you have some RAID Z VDEV right now with 5 disks in it, that's a RAID Z VDEV, but it's also kind of an AnyRAID VDEV where just all the tiles are mapped in exactly the simplest possible way. And so it would be possible, at least in theory, to convert that into an AnyRAID VDEV that has this sort of very basic tile mapping. And then you could stick new devices onto it and take advantage of that space. And we would have to detect what the furthest point is that's actually mapped in your RAID Z VDEV so that we have the free tiles at the end to do the balancing that we want. But something like that would definitely be possible. If we had our tile map able to fit in the new large label format or something like that, then we could do it without having to use that space at the start of every disk, or we could store a compact enough version that it would fit in this sort of other reserved space, and we could take advantage of that and do that VDEV conversion. So those are just some of the ideas that I had that I would be very happy for people to take a look at and think about and play with. And if you have more ideas, come talk to me afterwards. I'd love to hear them. That's sort of the end of the content portion of the talk. I want to do some quick thanks and acknowledgments. The whole team at Clara, I've been at Clara for about a year now. It's been a rad place to work. Alan Jude came up with most of the initial design of AnyRAID and then handed off to me to do the detail work on. Igor did a bunch of the user land and test work as part of the initial patch, and he was a fantastic partner to work with on all of this. Rob and Mateusz for doing the initial internal reviews and being great sounding boards and just generally being great to work with. Eshtec is the sponsor of the AnyRAID work. They're the ones who are paying us to implement this cool new feature and make it available to everyone. So I really appreciate them and that they're letting us and giving us the opportunity to do this. The OpenZFS community. I've been in the community for over a decade now, and it's been an awesome place to work. I get to solve cool, interesting problems with cool, interesting people. And so I'm really grateful to all of you and everybody who's out there watching and is part of the community. And the people who've already taken a look at the code review, at least a little bit, Brian, Alexander, Tony, and other people who've started to take a look at this. I appreciate your eyes on it. I would like more eyes on it. So anybody who's interested, please take a look and let me know what you think. I'm sure there are many changes to be made. Quick plug, Clara Systems. We do software development. We do solutions design. We do performance analysis. We do data recovery as a service for ZFS and FreeBSD. If you need any of these things, there are contact information here. You can talk to Alan. I think we're cool people to work with, and it's been a fun place to work. So quick plug. And then does anybody have any questions for me? I saw Mark's hand first.
Yeah, it's very cool stuff. So it strikes me that, there's echoes of what we did with DRAID work in this design. And it had a limitation, which you didn't mention, I think, as one of your limitations here, which is in order to, you do have to start with enough devices in your configuration to be able to have the replication level you're specifying in your configuration. So if you have, try to create one of RAID, your RAID Z 1:3, whatever, or 3:1, whatever it was, with 2 drives in your as a set of drives, that's going to fail, obviously. Yeah. That said, it seems really cool that you could sort of throw together a set of drives like this. I do have a couple of questions. One is, so, what happens, obviously, you kind of touched on this, when you get to the point where you are running out of space. Obviously, there's another limit there, which is if you can't find enough tiles across disparate devices to create a given instance of a stripe, you have to fail at that point. What does that look like? I mean, obviously, you can get to a point where you have space left across your drives, but you can't actually create a new tile stripe.
Right. So the way that that works right now is that when you create every time we open the VDEV, it calculates how many tiles it could possibly fit. Like it goes and does the allocation algorithm on repeat and says like, okay, this is how many tiles I could fit. And then it says, okay, so that this is the A size that I have available. And so that's just how much space the disk has available to present. And so you can't, like, right now it is an assertion in the code that's like, we must be able to allocate a new tile if you're doing a write at this offset.
Okay, that makes sense.
Yeah. One of the ideas that I had for how to get around the limits would be to do something about failure in that case where like you have to go back and suspend the pool if we run out of mapping space or something like that. But like that would be you're way down in the code when you're failing this IO that's in a way that's like really unpleasant.
Well, also, it does make sense that I think sort of doing the pre-mapping and saying this is the capacity. Could know what your capacity in advance is, I think, a very useful feature for a customer, for you anyway. Yeah. So one idea I thought, and it's the last part of this, when you were mentioning, the limits and the ability to, your limits imposed by the amount of space you're reserving for the tile mapping that has to put into the after label. One thought I had that you might think about is could you potentially do something like create sort of top level tile groups where you say, all right, this set of drives, it belongs in one tile group. Another set of drives belongs in another tile group, and those will actually be two separate allocation spaces. And so they'll have their own individual tile maps, and that way you could have unlimited number of drives by splitting them into multiple groups.
That is basically just creating multiple AnyRAID VDEVs. Well, at a conceptual.
So AnyRAID becomes the top level VDEV.
Yeah.
Yes.
Yeah. So you can create a pool with 3 AnyRAID VDEVs.
Okay. That actually falls out of just your design, is it?
Yeah. Yeah. Because the AnyRAID VDEVs are independent of each other. Yeah. Yeah, that does work. And there are tests in the test suite that are like, we can mix mirror parity ones and RAID Z parity ones as long as the replication levels all match up, or you use -f. Stu, did you have a question?
Yeah. So from an import-export time frame, is it gonna add 10%? 5%?
Imports are about the same speed. Like we read a little bit of this extra metadata, but in practice, it doesn't take very long.
Yeah.
Like the 64 megabytes that are reserved for the tile mapping are like the theoretical maximum. In practice, the space used is usually like 8 to 10 kilobytes until you start to get like a lot of drives or really big drives in it. Export times go up a little bit. That's one of the things that I talked about in the sort of performance work to do. But it adds like a second or something to an export. It doesn't like the time is relatively constant with the size with the sort of capacity of the pool. It just has to issue a bunch of IOs to all these different disks.
Right. It kind of goes back to what Garrett we were talking about previous days on, hey, we're talking 100, 200, 400 drive JBots. There's a break point where it might not make sense to do this, even though it's fantastic. But that quasi failover mechanism might be now 20 minutes instead of 2, or whatever that number is, just to.
Yeah, at large enough scales, there will definitely be some, like, the extra work that goes into seeing this metadata will take a little bit of time. There are a bunch of tasks that could be done to make it more efficient. The sort of initial version is very naive.
But to be fair, anybody that's doing those big ones are going to be consistent drives.
Yeah.
So, but
right. If you have,
I see the feature sets that I want to use, but I'm not the target audience right now.
Yeah. But, as you said, if you have 100 drives in a thing, it'll work. You may not be exactly the target use case. And so the initial implementation is not optimized for that, but there's definitely work to be done to make it more compatible for the future.
Very cool. Do you take into account drive and our peak by report of SC but is some size so either so or
Yeah, so the question was whether we take into account the health of the drive when deciding where to do our tile allocations. It doesn't in the current version. That's certainly something that can be done for the future. Although to some extent, I worry that, if we're trying to make that decision at like when we're doing these tile allocations, if the drive is only like temporarily having a hiccup or if it's going to get replaced with something else, where we do our allocations is sort of a long-term decision, short of doing rebalances that can move tiles around. And so making long-term decisions over potentially short-term health behaviors is not necessarily always going to be the right trade-off, but it's something that we could look into.
I also think one drive can degrade its the serological nature. So and the
I mean, so the parity. So, sorry, I think I need you to repeat the question a little bit.
yeah,
Okay, sounds good.
yeah.
How do you deal with the inconsistent tile maps? Like if you were updating all of the drives, right, half of them got updated, you lost power, then only half of them have the new tile map in it.
So the way that it works right now is it's similar to the way the labels work. If we find one copy where like all the checksums match and like everything verifies out of like a given transaction group, and like that's the highest number transaction group that we have in our copies, then that's the one we go forward with. As long as any of the drives manage to do a full sync, we'll use that newest updated version, and then we'll sync that. When we do another transaction group sync, we'll write back out to all the disks again. We read the tile mapping from like the first child first, but we'll try a bunch of different ones if we don't find one for the transaction group we're trying to import, or if it fails its checksums. And if all of them fail, like if none of them manage to fully sync it out, then we'll, in the same way that you'd have to roll back to a previous Uber block, we'll roll back to the previous TXG as part of the import process.
Okay, and a second question about, so labels are at the beginning and the end of the disk to protect, I guess, from some crazy bug where HBA will override the first part of a disk. Are tile maps similarly placed?
Right now, they're only stored at the front, but it's not a bad idea. We could do like 2 of the copies at the front and 2 of the copies at the back or something to keep those sort of spatially separated and a little bit more protected. That's not a bad idea. And now would be the time to do it before the initial version gets integrated. Yeah. Mm-hmm.
I'm really glad to see the fullest perspective.
That just use species. Let's say you started off with stasia chronology analogy about. Let's say you started off with a RAID Z1 actually, and then you decided that you wanted more protection. Could you add a big drive and start migrating to RAID Z2?
So this is an interesting question that I have thought about a little bit. And the answer is it's very complicated.
Yeah, as I started thinking about it.
Yeah.
The other use case is going backwards. So you've got a large array and you're running, say, RAID Z2 or RAID Z3. You're out of space. You have no budget. Could you start to backgrade to a lower RAID Z and to free up space?
So again, so part of the reason that this is complicated is because of the way that RAID Z works. As I had on the tile before, sort of demonstrating how it works, the way RAID Z like does its thing is it actually allocates like a single slightly larger contiguous chunk for the IO, right? If you have like a 1 megabyte write, it actually gets turned into like a 1 and change megabyte write to store the extra parity data.
Okay.
And so if you want to reduce the parity, you actually have to go through and like reflow in the logical space all of the IOs that you've done, because they're actually a different size now. And it, like, this is one of the things that that RAID Z expansion had to deal with, where like, if you increase the width, you have to like move all the data around. And I think as Matt explained when he did the talk for the RAID Z expansion feature, like parity changing is a whole nother level of complicated. Because I think you also have to rewrite the parodies themselves so that they work with the math differently, or maybe the first parody is the same, but like it's
It's better to do a send and receive at that point into a new.
yeah, it would be a lot simpler to receive the data. I won't say it's impossible because the computer's Turing complete; it can do anything we can tell it to do, but it would be a serious undertaking.
Yeah. Okay.
This is excellent work. Very impressed. I wish that we had designed this tiles layer of indirection into ZFS from day one. I think it would make a lot of the other features like flow more naturally. One minor point, you talked about having like each meta slab be on different tiles for simplicity, which is great. But I think it also needs to be on different tiles for correctness, because you can't have a block, like a single block. If it spans multiple tiles, then it might break the guarantees that we expect about like, each like for RAID Z, each part of the block being on different disks.
Right.
Makes sense.
No, it is certainly the case that there are multiple reasons why it is important that meta slabs all fit within a given tile. When I was first designing it, I was like simplicity, and then I thought about Nor, I was like, oh no, that would be a real problem. So yeah, it's important that everything fit within a single tile. Anything else? All right, cool. Thank you, everyone.